Hello everyone, welcome to my channel GATE-ISSR-VIZAG. Myself is Dr. ISSR. Started GATE training in the year of 2003, taught at various premium academies. In this session, I would like to discuss about process scheduling basics. So what is a process? Program under execution. Whenever a process is created, its process control block is also created. So main concept of CPU scheduling is nothing but selection of the process from the ready queue and send it to a run state. So why there is a necessity of the CPU scheduling? So CPU scheduling especially provides fairness among the processes. It reduces average turnaround time and average waiting time. Also, it increases efficiency of the CPU. So therefore, throughput can be enhanced and decreases response time. So CPU scheduling policy selection is based upon arrival time, job size, priority, and time sharing. So whenever a process enters into the ready queue, it checks that how many units a process needs. That means CPU burst cycles as well as IO burst cycles. A process may need both CPU burst time as well as IO burst time. CPU burst time is nothing but how many units required, how many units required by the process so that the CPU will get executed. And what is IO burst time? How many IO units required by the process so that IO operations can be performed? And total burst time includes CPU time plus IO time. But whenever we do CPU scheduling, IO time may be overlapped with the CPU time. So process execution is nothing but the combination of CPU burst time and IO burst time. So CPU scheduler. CPU scheduler, also known as a short-term scheduler, which is going to pick the process from the ready state and dispatch to a run state. Whenever a process is under run, then CPU get executed that particular process. As soon as execution is completed, the process will be sent to terminated state. Once it is reached to terminated state, the accommodated resources would be deallocated. And there is a component called dispatcher, which is going to especially dispatch the process from the ready state to the run state. CPU utilization. The concept of CPU utilization is nothing but how effectively we send the processes to the CPU and the CPU get to be executed. Therefore, n number of processes are executed at an instance of time. Therefore, throughput is increased. And the goal is that CPU is busy as much as possible, ranging from 40% a light load to 90% a heavy load. And whenever processes are switching from one particular process to other particular processes, then there may be a minute amount of time which is known as context switching time. For example, whenever you press Control tab, then that shows you that how many number of tasks are at present available. And you choose one task, then that task will be executed by the CPU currently. Then again, you pause the task and select another task, and that another task will be executed. For example, right now, you're doing some activity in MS Word and you minimize that and you would like to watch a movie, then you select the movie, then movie is playing. That means the previous task you paused and current task is live onto the CPU. And whenever switching among the processes, it takes some minute amount of time to pause the process. That means to load the previous context of the process into process control block, and that means save the previous process and load the context of the current processes is taking some minute of time, which is known as context switching time. And throughput indicates that the number of processes the CPU could able to complete it in a fixed amount of time. And CPU throughput can be enhanced, especially in time sharing systems. And turnaround time. The turnaround time indicates that So the entry time of the process and exit time of the process. And during this time, the exit time and entry time, during this time, the process may be busy with the CPU or the process may be busy with the IO. And that's why turnaround time indicates that exit time minus entry time. And what is the waiting time? A process is entered at so and so time and it left the CPU and so time. The a difference between that is nothing but waiting time. You imagine that a process is arrived at 9 o'clock and it left at 1 o'clock. But realistically, it requires only 2 units or 2 hours of time to complete that process. So rest of the time is getting to be what? Waiting time. So waiting time indicates that the particular process may be waiting due to some other process is executing by the processor, or the waiting time may be because you are spending some amount of time in IO queue or in the ready queue. And response time. The response time indicates that the arrival of the process and how at what time the CPU takes the particular process for the first time is known as a response time. So for example, many processes have come to the ready queue and CPU has to pick them. So whenever CPU is picked, then the subtraction, that means the difference between the CPU pick time minus the arrival time is nothing but response time. So response time is vastly increased or there is a good improvement in especially in time sharing system. For example, a process has come at 10 o'clock but CPU picks that process at 12 o'clock. Then what is the response time there? 12 o'clock minus 10 o'clock. That's the response time. For example, a process has come at 9 o'clock and the CPU picks that particular process at 9 o'clock. The response time is there, 0. And scheduling decision points. So scheduling decision points are nothing but so switching from a ready state to run state and switching from run state to wait state and switching from run state to ready state and switching from wait state to ready state. What does that mean by that? Let me explain with this particular figure. So imagine a process is initially in a new state and it goes to ready queue for some time. Let us say there are two processes by name P1 and P2. Right now they are in ready queue and there is a run state. So right now P1 is dispatched to run state. And here what I am going to do is I am using a time quantum manner. So time quantum is 2 units of time. Then P1 is executed for 2 units of time. Still it is not getting completed and P1 swaps back. Now P2 is given a chance for another 2 units of time here. So P2 is executed for 2 units of time. Here what happened? The particular process is switching from where to where? Ready queue to run state. This is the first condition. And the second one is that the process is created newly and it comes to ready queue and the process goes to run state. And unfortunately, the process needs some IO. And what happened here? So right now P1 is in the ready queue. Right now the P1 is in ready queue and P was in a run state. P1 leads to IO state for some time. Right now P1 is here. So here what happened? You're switching from run state to IO state. Once IO is completed, please look at that is the second point. So you're moving from where to where? First ready queue to run state. Then after that you're moving from where to where? run state to waiting state. And another one is there. What is another one? So when IO is completed, then the state is changing to ready queue. That means you're going from where to where. Again, you're going from waiting state to ready queue. That is the meaning of that. Waiting state to ready queue. And the other scenario is that the CPU is switching from one process to another process whenever you're executing multi processing system using the concept of time sharing. In such case, you are going from run to ready and ready to run. So ready queue to run and run to ready queue. Both are happening. So this is how the process is moving from one particular state to another particular state. So CPU scheduling decision maker. So number one, who is decided by the short-term scheduler, and the other one where the particular process is coming, that is nothing but ready queue. When when a process is moving from few states, I said, what is that? Initially, process is coming from the ready queue to run a state, and once the process is successfully completed, it goes to terminated state. Then that is the first one, run to terminate. And if at all the process needs any IO, then immediately you're entering into waiting state. That's the next one, run to wait. Once the IO is completed, then again you're going back, which is nothing but run to ready. And after that, whenever a new process is created, it is going to ready queue. And the other one, wait to ready. So wait to ready queue. This is a wait to ready queue. Wait to ready queue. There is no IO to run. There is no IO to run. So it is nothing but IO state to ready queue and frame ready queue to run state. So there are different CPU scheduling algorithms are there. Pure non-preemptive fashion and pure preemptive nature. So under non-preemptive nature, there is FCFS, shortest job first, longest job first, priority, and HRRN. Under preemptive nature, shortest remaining time first, longest remaining time first, priority based, round robin, multi-level queuing scheduling, multi-level feedback queue scheduling algorithms. So non-preemptive scheduling. What is a non-preemptive scheduling? When a process is entered into the CPU, that particular process never been suspended or preempted by other particular process. It has to release all its resources voluntarily, not by force. By force is nothing but you are imposing some force, therefore the process is getting to be paused. So the meaning of non-preemptive nature is nothing but whenever a process is entered into the run state, process must not be removed by force. It has to voluntarily release its resources once after completion that particular process, then it leads to directly to go where terminated. What does it mean by that? Even ready queue has got a different process like P1, P2, and P3. If at all the P1 is handing over to run state, so you cannot take out that P1 by force. The P1 must complete its complete execution until unless all its CPU time and IO time is utilized. Then it goes to terminated, then only P2 is handing over to a run state. But preemptive nature process is nothing but forcefully we will make the process to release all its resources. Therefore, I can able to give to other particular process. You take a scenario like this, there are different processes are there in a ready queue, and initially P1 is dispatched to a run state. Unfortunately, P1 has a lower priority. Then what happened? Whenever higher priority process by name P2, then immediately it suspends the P1. It suspends the P1 indicates that so you have removed from run a state and P2 get occupied. Now P1 is under this time pause because it is what? Preempted. So that is the meaning of preempting. Preempting is forcefully release the resources of currently executed processes by the CPU, and non-preemptive nature is nothing but voluntary release of the resources. So this is happened only when the process gets completed its execution by CPU time and as well as IO time if required. But preemptive is nothing but the higher priority process may suspend the lower priority process and get occupied the CPU. That is the meaning of what? Forcefully releasing of the resource of the existing process. And fairness versus enforcing policy. Fairness is ensuring that each process gets a fair share of the CPU and no process suffers from starvation. And policy enforcement, ensuring that stated policies like real-time tasks take precedency. So thank you for watching my video. Subscribe my channel for upcoming videos and click the bell icon for more updates. Thank you.